Hi, I'm Antonio Sala, and in this video we'll conclude the robust performance case study for this second-order process. In previous videos, we first manually solved the problem building generalized plants and manually searching for scalings, but in the immediately previous video to this one, we discussed myosynthesis, which is the way to go because many of the stuff we manually did, it's actually carried out transparently to us with the musyn command. So in here we will quickly review what we need to do, and we'll analyze and simulate resulting controllers, and we will also compare with a PID tuning with myosynthesis command. Okay, if we recall, we are solving a robust performance problem for this nominal process plus an additive uncertainty of size 0.5. Our robust performance goal is just keeping the closed loop set point to error response below the blue line for all plants, and myosynthesis allows us to solve the problem without manipulating uncertainty apart from putting it into the physical plant, in the sense that if we write this transfer function, well, without multi-incidents, just in case to avoid non-minimal realizations and repetitions of the uncertainty, so we have an uncertain physical plant and then we build the generalized plant as if we were solving a nominal H-infinity optimal control problem. So we wish to minimize the error subject to set point changes, and we have a 1 degree of freedom controller whose input is error and whose output is manipulated variable control action. So we build this generalized plant, and with suitable input and output weights, we build the weighted generalized plant as in nominal H-infinity problems, and musyn handles all the H-infinity plus scaled small gain stuff for robust performance. We just give the weighted generalized plant the number of sensors and the number of manipulated variables, and this is it. It iterates things and proves if this number is less than 1, robust performance. So the scaling here, it is called D, and importantly, it's a dynamic one. Why? Well, in previous videos, we manually sought a constant weight S minus 1 here, but if the uncertainty is linear time invariant, then it has a transfer function, single input, single output. So if I think of this as putting a dynamic scaling, which is also a single input, single output transfer function, then transfer function matrices in a general case do not commute, but they do in the single input case. So this is equal to this, and of course this is 1. So this justifies that from the point of view of blocks 2 and 3, putting a transfer function D and its inverse here does not change anything. Well, D must be stable and minimum phase, but okay, apart from those details, this means that we can use a dynamic multiplier, and internally it fits an 8th order scaling to prove robust performance. So of course this will be better than our manual trial and error search of a constant scaling we did in previous videos. However, this dynamic scaling has 2 drawbacks. First, it does not prove robustness to nonlinear or time-varying blocks, because then this delta of S will not exist. Nonlinear time-varying things do not have a frequency response transfer function. So this is specialized to linear time invariant uncertainty in robust control. And also the second drawback is that, well, the order of the regulator will increase because we are doing an H-infinity synthesis problem with things of order 8 plus our generalized plant that was 3rd order, 2nd order physical plant plus 1st order error filter. So at the end, we have 11 states in our controller. So this is the idea. Myosynthesis with dynamic weights may yield a high order controller. In order to get simpler controllers, we have three options. Either look at the documentation and tell musyn via some options to reduce the fit order of the scaling T. We will not do it for brevity. It's easy, look at the mu synthesis options in Matlab's help. But we will discuss the first and third options here. First one is using standard order reduction techniques to get down from 11 to something more sensible. Or we can use musyn to tune a fixed structure controller such as a PID. So we will do it and compare. And perhaps unsurprisingly, we will realize that a PID will be a very good option for this second order process. Because we know from, intuition, our undergraduate courses, that second order plants are very well controlled with PID regulators. So let's first reduce the order. If we see the Hankel singular values for balanced order reduction, we see that from the fourth or fifth maybe onwards, they are very small. So a third order controller will possibly do. And indeed, if we use balred command to get to order 3, then if I close the loop of the weighted generalized plant and this reduced order controller, then I get a worst case gain, robust performance measure of 1.0005, which is basically 1, so this is satisfactory. If I used a second order controller, then things will be much larger than 1, so second order balance reduction is not an option in this case. I go back to third order, and now I can further reduce the order by thinking that, my system is s+1 squared denominator, so what the hell does this pole at almost 700 radians do here? Well, not much. And this thing in there, it's kind of very high frequency stuff. So maybe this is not relevant. Well, balance reduction could not delete this extra dynamics, but if I do it with frequency separation, freqsep, with a cutoff frequency of 150 radians, then I get a slow component with sensible poles and a fast component that I will just forget about it using only its DC gain. So if I add the slow and the DC gain of the fast component and get a second order controller, the miracle happens and I get worst case gain less than 1. So we have guaranteed robust performance with this second order controller. So we successfully reduced from 11th order originally to second order as our final result. If we look at what we have obtained, then we get this thing that closely resembles, if this were 0, this will be an integral action. This filter at 5 times my plant dynamics may be a noise filter in PID jargon, and this will be, proportional derivative and integral gains. So this really looks like a PID controller. So this hints that maybe we could have optimized from scratch a PID controller instead of doing this reduced order stuff. So let's try it. And the direct mu synthesis optimization of a PID regulator is done by crafting a tunable PID, closing the loop with a weighted generalized plant, and telling musyn to use whatever robust performance theorem, scale, small gain, etc. it needs to tune the controller gains. So at the end, it also achieves, apart from the fourth digit, let's say, it also achieves basically the same level of performance than our 11th order reduced to 2 previous version. So this PID will also be a satisfactory design, and if you sell PIDs to your customers, they will be much happier than if you sell high-order state space controllers. So we are happy. These are the gains and filter time constant it decided. And in fact, if you see the PID pole 4.9 and the PID zeros 1.2 and 0.9, well, and of course the integrator, this transfer function is very similar. 0.9, 1 point something, 4.9, it's quite similar to the result of our new synthesis, reduced order, balance, freqsep, etc. So these are two ways of obtaining basically the same, because indeed we have an underlying second order physical plant. So intuition tells us that PIDs might be very good for my second order plant, and indeed they keep up to the promise, and we find a tuned PID with robust performance. Okay, it should be below 1, it's 1.0009, but okay, it's good enough for us. So if we close the loop with the PID and we do the step response, we get this step response. The blue lines refer to the plant used for design, which may include very high frequency uncertainty. So I have these instant jumps to here, and the red lines are simulations in which I intentionally did cut the high frequency uncertainty, so all of them start in 0. So the uncertainty gets here, but regarding settling time, rise time, etc., all simulations in this part of the plot are roughly similar, and that's what we were seeking in our robust performance problems. If we see it in the frequency domain with this BOTMAC stuff, all blue plants are below the template, the thick line, and of course if I trim the high frequency uncertainty, then I get less strange things at very high frequency in the red plots, but okay, a guaranteed robust performance. The design plant is the blue one, even if the red plant is my simulation, because I do not believe there is so much high frequency uncertainty. But just in case it is, I designed for the blue line to be below the template. That's robust performance. So I get this robust performance with the PID and this step response. And I also need to look to the manipulated variable with this step response to check that we got a sensible controller tuning, because nothing strange happens, and indeed I don't have a lot of saturation, only 1.1 maximum amplitude, and things seem reasonable both in time and in frequency. I don't see absurdly large peaks or high frequency response of my controller, so I am satisfied. If I now execute with the mu synthesis reduced order stuff, I will get basically the same, because the controllers were basically the same. Indeed, nothing too different happens from a practical point of view in time or in frequency domain regarding loop error, and again in time and frequency domain regarding manipulated variable. As a last observation that has nothing to do with mu synthesis for the moment being, but okay, it's an interesting connection with previous stuff. As I had an additive uncertainty of size 0.5, then robust stability small gain bounds will tell me that the transfer function from set point to control action times delta must be less than 1, so if delta is less than 0.5, then this thing must be below 2, 6 dBs in logarithmic scale, and of course this thing must be checked for the nominal g. Okay, this must be the nominal g, so if we plot this curve for the nominal case, replacing here just g, the nominal transfer function, we have this, so this will be the robust stability bound, and this detuning, this extra limitation on the control action gain is what we need to achieve not only robust stability, but robust performance. So this is it. We concluded here. In this video, we analyzed a mu-synthesis controller result, and when the controller was in arbitrary state space, it had a high order, so we reduced it to order 2, and we also tune a PID, obtaining basically coincident results. So this is it. Thanks for watching.